So this is the fourth webinars we have in this series that we started early January. So this is a new special interest group that we have in IEEE that is called Beyond Diagonal Reconfigurable Intelligent Surfaces. That was established a few months ago, and then we initiate this first webinar series for 2024. And so this is our fourth speakers today, Professor Ross Murch from HKUST. Next slides, Matteo, please. So Ross is a very well-known figure in the community. I don't think I will go through the entire CV of Ross, but he's a chair professor at HKUST, so Hong Kong University of Science and Technology. He received his educations from University of Canterbury in New Zealand. And I think he's been at HKUST for quite some time. He's very well known in various areas of communications, where he did a lot of work on multi-user MIMO and OFDM in the past. Then he did also a lot of work in radio antenna and RF design, where he's quite active nowadays in this area. So he has a quite broad understanding of both communication theoretic principles, but also more antenna and RF designs. And so he has the ability to really bridge those two communities in a way. He's been distinguished by many awards in the community, and he's been active in various countries for various committees. You can see from the extended resume. So a few rules before I let the floor to Ross. So the talk will be roughly 50 minutes long, and the audience will be muted during that time. If you have any questions, please feel free to type them during the chat, and then at the end, we'll answer those questions. You will have also a chance to raise your hand and to be unmuted if you want to ask your questions orally. Otherwise, we'll ask questions from, we'll address the questions that actually are listed in the chat. And with this, please enjoy the talk. And Ross, the floor is yours. Thank you very much.
Okay, thank you, Bruno, for your nice introduction. And indeed, good afternoon to many of you, and good evening to people where I am. And also good morning to everybody else. So let me first share the screen. And then I need to, I think everybody can see that?
Yes.
Okay, great. So today I'm sort of focusing on the implementation of reconfigurable intelligent surfaces. So just looking at some of the issues behind their prototyping and making. As Bruno says, I try to sort of span both fields, systems and the electromagnetic fields. So it's good that I can know a little bit about both, but on the other hand, it might mean I actually end up knowing nothing about either field. So there's a lot of material that I cover. And first off, I think I need to thank my research team. Now, currently, I have quite a few students, and this is a picture of them from last year. So many of the results you see today are from some of these, and some of the students have also joined this webinar. So I also get funding from Hong Kong government, and also thank you to collaborators who I've written papers with in the past as well. So as you can see at the right-hand bottom corner, that's a picture of the university. I live and work in Hong Kong, and I'm not sure if you know much about Hong Kong, but you can see the university is in a beautiful place and has beautiful views and a very nice location. It's a great place to work and study. So in my talk, I would like to go a little bit of background, more general than just RIS, a little bit about how I see the world, and then move on to some of the challenges and key points. So I want to first start off with reflecting RIS to give you an idea of the difficulties and our work. In terms of the beyond diagonal, we look at star ones. So we have less progress here because it's somewhat harder. we have found, but I would like to give you some of the insights that we have got from that. So let's start. So with the background, so the way I see the world of wireless is that we have radio, we have TV, we have cellular systems, we have Wi-Fi. There are essentially many, many radio sources everywhere. So basically, no matter where you are, what you're doing, there's always some RF radiation around you. And I call this the fog of, or the wireless fog of RF waves. Basically, it's different from 50 years ago. 50 years ago, RF waves were not everywhere, but today, no matter where you are, you can always get access to RF waves one way or another. And I see this as a new resource to be harnessed. And to better understand what this resource can do for us, we can compare it to an analogy with sunlight. Sunlight is also essentially everywhere when the sun is shining. And we can do many things with sunlight. And we can do imaging, collect energy, heliostat, a heliostat and sextant, heliograph. A heliostat is like a mirror for brightening up your room. So that's very similar to RIS. Sextant for navigation. Heliograph is for communication using sunlight. It's a little bit like ambient backscatter communications. And so the way I see the world of wireless is that we can try and do the same and more for wireless, for RF waves. We can do imaging, communication, navigation, energy harvesting, and perhaps we can even think of new applications. And basically, my area of research is creating new RF wave technologies, and at the moment, trying to do that for 6G. And so basically, RF waves can be used for much, much more than just communication. And the way I develop this area, I try and look at all of the issues together. And so some of those issues are what I call wave shaping. So this is like RIS. Wave sensing, this is like imaging, and wave characterization. So this is like understanding propagation and so on. And furthermore, if we can shape or control this RF fog or wireless waves, we can use it for our own purposes. And that's one example of RIS. If we can sense the fog and we can estimate the environment it's passing through, we can do imaging. And if we can characterize it, we can use the properties to better sense and shape it. So these are kind of the fundamental building blocks that I think we can classify nearly all the RF applications into. And maybe looking at RF waves in this way allows us to maybe see new ideas. So in this particular talk, I want the focus to be on the wave shaping part, so RIS. And I have stolen or borrowed this picture from Bruno's paper, which is cited on the right there. And in this talk, basically, I want to sort of focus on two of the particular RIS designs that we have. I'll just shut my window since some alarms have gone off. There was a car park below, and car alarms never go off. But today, when I do this talk, yes. Anyway, and one example as well from Bruno and Shampoo's work is the cell-wise RIS, where waves can come in and they can actually pass through this RIS. So we'll look at this one and also the reflective type of RIS in this talk. So basically, what is the talk target? Introduce the implementation of our RIS structures. As I said, I span both the worlds of wireless and electromagnetics, and I'd like to just try and give you some insight into some of the issues in this bridging area. And another way to think of it is report some of our struggles. it has not been easy to prototype RIS and also report our results with implementing them. So some of the work's been quite hard, but of course, it's very interesting to see where we can get to. So first off, let's look at some of the challenges in RIS design. The first challenge is the bandwidth and incident angle of the waves coming into RIS. Scattering depends on frequency and the incident angles. And in this graph here, what we have is some results from an actual RIS that we have made. On the left axis, we have something called phase entropy. Loosely, it's just basically a measure of the phase characteristics of our RIS. And the blue lines are for frequencies of 2.35 to 2.45 when the incident waves are coming directly in it. And as you can see, for these frequencies and angles, the characteristics of the RIS are fairly constant. But for a little bit increase in the incident angle, we can find that the phase characteristics or reflection of the waves from the RIS deteriorate at the edges or at the large angles from the RIS. So this is often in system papers, you assume that it is a perfect RIS, but in reality, certainly at the wider angles, the characteristics of this device change. And it's also extremely difficult to get more than about 5% bandwidth. And this is because at bandwidths bigger than this, the phases will start to change quite significantly. And so we have some more challenges with that. And of course, another aspect is if we want to make dual band RIS, how do we go about it? And if we use a dual band, then both of the bands must be independently reconfigured. So also leads to more challenges, and perhaps you can put in two RISs together. So definitely bandwidth and the angle of incidence of the rays coming into RIS are a challenge when we actually make them. Another issue is the antenna radar cross-section. Often we make RIS from antennas, and one of the characteristics that we use is the antenna radar cross-section. And basically, this is the amount of electric field scattered by the antenna when we have a certain load connected to its input. And we get what we call a structural and a scattering antenna mode, so a scattering mode. And so on the right here, we have a picture of 1, 2, 3, 4, 5, 6, 7 antennas. And if I have all these antennas open circuit and I put a wave come into it, then even though all the antennas are open circuit, there will be a certain reflected wave from this device. And then if I load the ports or one of the ports by an impedance, ZL, then the actual scattered waves will even be higher. And so this is what we refer to as the radar cross-section. And of course, the thing we want to do is make the scattered wave as large as possible. In my work, I define the structural mode as the open circuit scattering from the antennas. In most other definitions of the structural mode, it's either loaded or short circuited. I prefer this open circuit definition. And this component cannot be controlled, and it depends on the ground plane and the design of the antenna. So the structural wave, the RIS can never control it. And if you've ever wondered about antennas, if I have a 50 ohm match, in principle, you'd think half of the energy is not reflected, it's absorbed by the antenna because the antenna has a 50 ohm match. But because of this structural term, this is not true. So half of the energy is not reflected because there's a structural mode. And this structural mode depends on how big the ground plane is. If I made this copper material much, much wider, much longer, there'll be a much bigger structural mode. So this mode we cannot control, so it's not much interest to us. the one we want to control is the second term. And basically we want this term to be as large as possible, and which basically means this one should be as large as possible. And essentially means that when we put waves incident to our surface, we want as much of the waves to be reflected as possible. And it depends mainly on the efficiency and the directivity of the antenna. And you can find out a little bit more. We did some work on this quite a while ago with energy harvesting, working out what conditions allow us to harvest the most energy. So what does this mean? So, of course, we want to make that absorbed load, the reflected power, as much as possible. And it essentially means that the antenna pattern must be constrained to be the front of the RIS. If the scattering pattern of the antenna has a back lobe, so like this, so this is our antenna here, and this is incident wave coming in and being reflected. If it has a big back lobe, then this is basically wasted energy, and the directivity of this element will be too small. And this is particularly important, I think, for the star RIS, because this back lobe will affect how much radiation is put through the device. So if there's significant side lobes or back lobe, less collection of energy and less radiation in the directions we want. So we have to be careful that we also design the antenna characteristics properly. And for example, in this device, then if we want all the waves coming in and then being reflected, we have to make sure all the antennas have a very nice radiation pattern. And another issue is efficiency. The efficiency of antennas, we know all about them, but the phase switching characteristics are quite lossy. It's very easy to lose 3 dB in the phase switching, and 50%, it corresponds to 50% of the received power. And so basically you want to reduce the switches or use other approaches, and one way to do that is to design our system slightly differently. But to give you a better example of the switches is we have made a phase shifter here with 4 states, so 0, 90, 180, 270. And the one-way loss through this device is somewhere between 1.7 and 2.1 dB, depending on the frequency. And so if we have a wave coming in and then going back out, the total loss will be double this, so more than 3 dB. So more than 50% of the energy coming into our RIS is actually going to be lost in these phase shifters. And on the right here, we actually have some prototype phase shifter. And you can see more details in one of our publications here. So this is quite significant. This loss, 50% of the energy going missing is quite significant. Another thing is mutual coupling. We want to increase the number of elements to increase the reflected power. However, the RIS size needs to be increased. So mutual coupling needs to be kept low. Otherwise, we get side lobes. There are many methods to reduce mutual coupling, and we have some results here, but can also be quite intricate to prevent the mutual coupling. In principle, we can show that we can get about 20 elements in per square wavelength if we pack them correctly. A final challenge is one that we often don't think of. If we let n represent one of the n states of our element, so maybe our element has n different phases possible, then we define a state separable system as one where the characteristics of our RIS, the reflection and incident waves, are dependent on just theta and theta s and this wave or this phase shift. And the phase shift depends only on n. That is, the characteristics of the antenna do not change when we change the state, the phases of the system. But there are RIS, and I'll show you one later, where it's not separable. that the phase and the antenna characteristics are not separate. So here they are separate, they are a product, but here they are combined together. And I call these non-separable systems. And so, no, I don't think anybody considers systems like this. And basically, one example here is on the right. And here what we have is, if I take one of these colors, like the green, this is the phase shift we get from our RIS if I have a signal coming in, say at 0 degrees, and I measure the phase at all the scattered angles. And you can see here for the green one, it is fairly much straight. But if I want to change the phase shift to be, say, 270, then we can see that its phase characteristics are maybe at 270 at a certain band of angles. But it's not constant, and this curve is different from this curve here. And so actually the shape across these angles changes. And so therefore, to properly characterize the RIS, we need to have this sort of non-separable model. And so this is a big departure from what we would normally consider. So big impact on channel estimation. We have to do many more systems. So separable systems, knowledge of one state reveals all the states. But non-separable, we need knowledge of all the states. So this is quite a significant difference compared to normal systems. So that's that. Sort of a brief introduction to some of the challenges that you may not think of when you're actually looking at the system. And so now I would like to sort of go into some prototypes that we have made. So I'll go through them fairly quickly just to highlight some of the key principles that we have used during the system development. So for the first type, for the RIS that are reflecting, I will just give you 2 designs that we have published and implemented. The first one is just a reflecting one, and it's now been published in the MTT. And basically, it's just a usual conventional RIS. And instead of using phase shifters, like the ones I've just talked about, we actually use elements in which we add switches to the sort of the inside of the element to change the phase. So we try and reduce the losses. So each one of these squares here is actually one single element. So this is like a 4x4 RIS. But we do not use any phase shifters. We actually change the connections using switches on these elements. And then the second one I want to introduce is an active RIS. So this is based on antennas, but the novelty of it is that we actually have reflection amplifiers behind it with phase shifters. So when the wave comes in, they get amplified and phase changed and then get transmitted out. And so there's been some work on active RIS, and this is actually a prototype of one that we can experimentally get its performance. And let's first look into this, the passive RIS. So it just has phase shifting. And we'll look at one particular element and work out how to design it. So these elements, they have high reconfigurability, 16 different phases. They work below 6 gigahertz, single polarization, and they work for a wide incident angles. And the first thing I think you always wonder about RISs and electromagnetics is, how do you model them? And usually you think you need to know electromagnetics and so on to model them well. But in principle, this is not the case. If you look at this surface here, you can see it's actually, this is one element, and so we've broken down the surface into many sub-elements. But there are many kind of inputs or ports between all these elements. And actually, we can just treat it as a linear network. And if we put it as a linear network, I can write it as a matrix, and then I can find the currents and so on that would be flowing through the connections if I put loads between them. And so what I'm saying is that electromagnetics with Maxwell's equations looks complicated, but in fact, as a function of E and H, electromagnetics is a linear system. And so it can simplify it down to linear equations. And this is how we model our RIS. We get this impedance matrix, we add in the loads, and so in this RIS, we short some of these components or some of these elements with a switch. We leave some open, and then we actually hardwire some of them. And a hardwire would make this 0 on the load. An open would make this infinity. And if we have a switch, it would be either on or off. So it could be very low impedance or very high impedance. And then with that, we can find all the currents flowing through this surface just by doing a MATLAB calculation. And then we can find the radiated field. And it may sound a little bit too simple, but in essence, that's all we have to do. And we can find the radiated field also by a relatively straightforward calculation of knowing the currents and the patterns. And it's very fast to calculate. So we can actually calculate the field scattered by this RIS very, very quickly, just through a few simple linear calculations. And I think this is the key to doing electromagnetics from a system perspective. In our particular design, what we want to do is control the phases across the surface. And so maybe we want to have qubit control of each element, so 2 to the q different phases. And if we do this, we define an objective function that we have referred to as just phase entropy. So it's defined very simply, similar to information theory, but it's simpler than that. All we're trying to say is that we want a function that tells us how separated out the phases are of our RIS. So basically, we calculate the scattered field and the different phases of the different configurations, and we say it is good if the phase entropy is as large as possible, which just means that they're evenly spaced across all 2 pi of the phase shifts. And so if they're evenly spaced like this, entropy is high. But if they're all bunched up in a very small phase shift, they have this low phase entropy. So it's a very easy objective function we can use to optimize our surface. And if we just take one element, if we do this optimization, we find that if we put a shorts between these elements, no opens here, and we put in 4 switches, then we can produce 16 different phases spread across 0 to 2 pi. And these switches are made from diodes, and they have a certain model that we also include in the load. And I just want to go back to this idea of the modeling of electromagnetics. It doesn't need to be difficult. We have produced quite a lot of designs. This is antenna design. This is a multi-port antenna. This is the RIS that I'm talking about. And this is also some antennas where we have improved the mutual coupling and polarization by adding in these sort of substructures. So the actual antenna is here, and that we've split down the structure into these small, what we call pixels. Just like in our RIS, this is one element. And inside the element, we have divided up into these pixels. And when you do this, you can just use a conventional simulation program and run it just once, find the impedance matrix, and then you can put it into MATLAB and do all your electromagnetic calculations very simply. And all these designs have been found by this process. So basically, we do it in MATLAB just using a very straightforward linear calculations. And if you want to know how to do it, this paper here is actually pretty good. It includes all the details I've just talked about. I think Yuji or Jerry is actually in the audience if you wanted to ask a question about this. And the optimization process, also quite straightforward. If you know Daniel Palomar, he's an expert on convex optimization. He has also helped us develop optimization algorithms for this approach. So this is when you put 16 of the elements together, so this is one element, and we can have 16 different phase shifts, and we can put them there into an array of 16 elements. We can find its performance. And so each element has 4 switches, so there are 64 switches. So there are 2 to the power of 64 combinations of phases that we can have. And if I have a way of coming in at, say, 0 degrees to my RIS, then this is a plot of kind of the 3-dimensional reflected wave. And we can see here that, no, it's going to, we can steer it off to the left, upper left, or we can steer it up to the top, or straight back, or down to the right side, and so on, simply by changing the configurations, switch configurations on each of these elements. And these colors here on the elements refer to the switch configuration. So basically what we're saying is, if we have a beam coming in at any angle, this surface allows us to reflect it back also to any angle, which is some of the things that you want to do when you make a reconfigurable surface. And this is some more examples at a different angle. Just some additional information, sort of some of the background information when you make things like this. These elements are reconfigurable. And when it's reconfigurable, there are switches inside. Whenever you have switches, you must have digital circuit connections to turn them on and off. However, so on the back side of our RIS, we have control lines. And because on the back of it, on the surface, we don't have the ground plane until it's further back, these control lines would actually affect the RF performance. But the way we can make them invisible to the RF is to put inductors or chokes inside here. And so even though we have a wire, it only operates at DC. And at the AC, because they are at RF, because there are RF chokes here, it is effectively invisible. So even though we have these wires passing through the RIS, they have no effect on its performance, or very minimal effect. And so this is one key thing when we design RIS, how to put in these control lines. And if you make them like this, so these very small elements with inductors between them, they can be completely invisible to the RF, but be used for DC control. And on the right here is our prototype RIS, and the backside of it is here, where you can see, if you look very closely, the little wire segments, but every little gap there is a RF choke. And this is being tested in the lab, and so we have our RIS, and at the back we have an FPGA that controls all 64 diodes, transmitter, and then a receiver. And no matter what angle we put in this transmitter, we can always make sure that there is an array reflected out with a different phase in any direction we want. So it is completely controllable scattering. And so we can use this for our as an RIS, and more details can be found in this work here. So I'm happy to share the slides to anyone who wants them as well. You just need to maybe ask me by email. So one key point with this system, though, is actually an example of a non-separable system. So even though we prototyped it, it turns out it's not separable. So this means, as I've said before, that for one configuration, the phase may be reasonably constant across different instant angles, but at a different configuration, it can be completely different. And so the shape of this curve cannot just be translated. And so this means, this is a surface that I don't think system people have even have actually considered before. Whether it's practical or not, not sure, but this is one type of system that we are thinking we should include it as a possible example. So just quickly, looking at a active RIS. So in this one here, we've based it on antennas. So signal comes in, we change the phase, and we send it out. But when we change the phase, we also amplify it. And in this work, you can find more details and also published in another paper One of the very unique things about this is that the signal comes in, it's a reflecting amplifier, it reflects it back and passes it out through the same port. And so it's what we call a reflection amplifier. So it amplifies and then reflects the signal back. So it is quite difficult to make. So this is some of the prototyping. This is the phase shifter and amplifier, and we can achieve 8.5 dB gain and good phase control. And when we put it in a circuit, we can measure it, and we can also find its characteristics. And so we can form beams, and typically the beam will have about up to 10 dB more reflected power or output power compared to when we turn the amplifier off. So we're able to get a good increase in signal strength by having an active circuit. So whether this is useful in practice is not clear, but there may be some new types of RIS systems that we can develop using active circuits. One key point to note with this is that because we made it from antennas and phase shifters, it is actually a separable system. So this is good news. This means that it obeys all the types of assumptions that you make in a systems paper. And as I said, you can read more about it in one of our papers works. Okay, so that's some of the background to RIS. And now I want to describe how we are trying to make some star-based RIS. And so you said at the start here, I said that the focus of this talk is implementing RIS, and then the scope is the struggles. So I think they're all difficult to make, but this particular star one has been particularly difficult to make, much more difficult to make than I would have guessed. And I'll explain why we've had such trouble. So for a star RIS, wave comes in, some of it's reflected and some of it is transmitted through the surface. So it does a reflection and transmission. So it is obviously more complicated than the traditional reflected one. And one of the key things is that the reflected wave can have any phase and any magnitude. The transmitted wave can have any phase and any magnitude. But the total power must be conserved so that the reflected power plus the incident power plus the transmitted power must be equal to 1. So everything can be adjusted, independently controlled, but we must obviously satisfy the conservation of power. So this is quite difficult to make. So the first simplification that we do is that we just reduce it to 3 modes. So one mode is entirely reflective, but reflective with 2 phases, 0 or I, or entirely transmittive, also with 2 phases, just 0 or pi, and finally a hybrid mode. And in the hybrid mode, half of the energy is reflected, half is transmitted, and the reflected can have 2 phases and the transmitted can have 2 phases. So in total here, there are 8 configurations, 4 different phases here, and then 4 different phases here. So 8 configurations. And this is a simplification of the general case. And then when you simplify it, now how do we make it? And so this is a general sort of description of how we make it. So we could have, let's assume we just ignore the polarization for a bit. We have an antenna, it receives a signal. We would then do phase shifter for reflection, split the power, and then phase shift for transmission. And then we would transmit the signal and also reflect it. So how do we make that? Well, it sounds pretty easy. And if you read our papers, then we can just have a very straightforward network like this. So just made up of a pi network made up of 3 components. And if we have grouping where some of the signal can also go out other ports and also be reflected, then also perhaps a relatively straightforward network as well. And this is the problem. So you get to this point, you think, okay, easy to make. We just make this network. But the problem is when you start going into the details. When you start going into the details, we can do the analysis. And if it's a n-port lossless network, then these are some of the characteristics of the network that we must follow. And for the 2x2 case, in other words, the reflected voltage can be anything, and it can be any phase, but the voltage that passes through must follow this relation to make sure there's power conservation. The key thing here is that the phases can be arbitrary. And then we can find the matrix that we want to satisfy, and then we can compare with a pi network to find all the impedances or reactances or admittances in our network. So sounds straightforward so far, and so far so good. But next step is, how do we make these impedances reconfigurable? Well, we can make them reconfigurable with varactor diodes. So varactor diodes, they can change their capacitance. And so with a varactor diode, in principle, we can change the reactance from any particular value. And if we do that, which is very good, then we find that with diodes in practice, you could change the reactance from -100 ohms through to J 100 ohms. So, okay, sounds good. So far, so good. But one further step is now, if I actually put in realistic diodes, I find that I can model it, and everything is good. So this is the model for the diodes and the reactances, and we can find 8 states. So basically the states that we want. And this is the range of capacitances that we would need, and also the range of reactances that we would need. So all quite manageable. Now, one aspect here is that the bandwidth is quite low. And the reason the bandwidth is low is because the phase changes quite significantly for small frequencies. But even more importantly, what we find is that in reality, there's also a very small resistance in the diode. So it has a very small loss. So just a very few ohms, 1 to 2 ohms. And even though that is very small, this parasitic resistance degrades the target performance significantly. Too much insertion loss, so too much power goes missing, and we cannot even meet those 8 states. We cannot control the phase well enough over the bandwidth. So basically, what I'm saying is the approach like this cannot be made in practice. So cannot be made. And so when we started making these star RIS, we went down this path, and we've spent many months fiddling with them, trying to get them to work. But in the end, we decided, no, it looks good on paper, but this is not how you're going to be able to make these things. So quite a significant hurdle for us. So how do we make it? Well, we have another approach. And so another approach is that we do not try and make it with a network. We split it up. So we first do phase shifting for reflection, a power splitter, and then phase shifter for the transmission part. And so we do not make it using that network at all. We just do it as separate components. And we can also do the grouping one in a similar way. We have power coming in and out. But let me focus on the single cell one. And so essentially, when we make our single cell, we have a phase shifter, and we make it by delay lines and a switch at one end and a switch at the other end. We then have a power splitter, and so we can make the power splitter relatively straightforwardly, and then we have another phase shifter. And these phase shifters here must be 2-bit phase shifters. So both of them must be 2-bit, so 4 states. And the reason for that is that this allows us to have 1-bit independent control over reflection and transmission. And the reason for this is that when we change the phase here, that's very nice, the energy will come back, but it also changes the phase of the signal that goes through. And so this phase then must change along with that phase, and that's why we need so much control, simply to get 1-bit phase difference. And this is quite feasible to make. And so you can't make it with a network, but you can make it with this type of approach. And if we put it together, we have our phase shifters here for our implementing it. And when we put the whole thing together, this is an antenna with phase shifters, and then we have our power splitter, and then we have our phase shifter, and then another antenna. And we can see that the performance across about 5% bandwidth, so something like Wi-Fi, is fairly constant, so that the reflected wave is fairly useful. I don't know what happened here. I'll just share the screen again. I think something has happened. Sorry about this. And so this here is a feasible design for one cell of a star RIS. So cannot be made via the network impedance, but must be made in a slightly different way. And so this is what's taken us so long to actually get through to make this thing. So we can also have more complicated ones where we have 2 ports. And so this is like a grouped system. In our system, we also have some polarization change. But for a full 2-port system, a little bit extra work needs to be done. And we've simulated them in 4x4 RIS, and we can get full reflected wave, we can get half power front, half power back, and we can also put some power at different directions on our star network with this kind of surface. So we can definitely show it can do all the required types of beamforming. So just to quickly finish off, I know I'm running out of time. Key point summary. There are some significant implementation issues. We can make lots of different systems, but without taking into account some of these aspects, our designs will be a bit limited. So efficiency is one thing. We have to assume we'll lose 3 dB in the RIS. Bandwidth, cannot assume it is like very wide band. Things depend on the angle. There's mutual coupling. Is it separable? Is the radar cross-section large enough? And star RIS brings another level of complication. Impedance network is not implementable, limited reconfigurability, and the backload, of course, needs to be known to low. And the grouping case, cells with more than 2 antennas, has yet to be well explored. So that's another challenge for us. So before I finish, I just want to also give a couple more results. Wave technology is more than just RIS. We can also do RF imaging. And if you look at this picture, this is an office environment at the university, and we have Wi-Fi boards, actually quite a lot of them around this area. And so we want to image inside here. And in particular, we want to work out whether these books have been moved or not. And with this approach, we can actually use, so this is actually image experimentally, these books. So this is the ideal location of the books, and this is the reconstructed one. And this is its permittivity. So not only can we find the location of the books, we can also estimate their permittivity And in our method, this is one of the unique things that we can find the location, but also estimate the material type, and more details are here. So another thing of this RF wave technology is ambient energy harvesting. And if you look at the picture here on the right, is a mobile base station here, about 50 meters away from our energy harvesting RF system. And this is a window, and then this box sits in front of the window. And in our box, we have antennas, rectifiers, and a Bluetooth system, and so on. And the waves from this wireless base station is enough to be collected and power up Bluetooth, such that it can transmit the humidity and temperature sensed on this device and send it about every 15 minutes. And so this is an example kind of like of a RF solar cell. And you can find more details here. So that's where I want to finish today. And again, thank you to my team and collaborators and some funding. So thank you very much. That's basically what we have in terms of the experimental results.
Thank you very much, Ross, for the very informative talk, actually. I think it's the first time I see discussions on this RIS implementation, especially the star RIS implementation. So I think the insight on the use of these reconfigurable impedance networks and whether we can implement this, I think this is quite insightful. Do you have publication already on the star RIS implementation, or actually?
Yeah.
Is it available?
Yeah, unfortunately, not quite. So these are quite preliminary results. We're trying to write them up as fast as possible, and once we've written them up, we will actually put them on public access, one of the like Tech RF or Archive. So then maybe I can send you the link for them. So one of the students working on it, Zhao Yong, is actually listening to this talk. So hopefully he gets motivated to write this thing up faster so we can put it on Archive.
Yeah, this is very helpful. Very, very interesting. Great. Any questions? We have a few minutes. I think, okay. Hamad, do you want to raise your question?
Yep.
I think, Matteo, you can maybe unmute.
Hi, Ross. Thanks for the informative talk. So given that the purely reactive impedance network cannot be realized in practice, can we introduce some active components to overcome the losses?
We could. Yes, I don't know if I have a good answer for you on that. The moment you put active components in also brings with it a lot of issues as well. I guess one of the things is, how do you power it up? And then if we put active components in there, you may need also to include filters in the system, because if I have an active component that is doing some amplification, if there's a signal outside the band, then it would also might amplify that. So then we need a front-end filter. So when we have an amplifier or something of this nature, it can add a lot of complication. So I did discuss the active RIS earlier, and it's just a demonstration of what could be done, but there are a number of other issues. And I think one of them is you need a front-end filter to make sure signals on other bands are not also amplified by the system. So yes, probably you might be able to overcome it, but there would be some other issues that would occur because of it. So two of my students are here, Jun Wei, and also, as I mentioned, Zhao Yong, and they're welcome to add something if they want to say something as well, but they probably may not. But I think that's the best answer I can give for now, Hamad. A good question.
Thank you.
Thank you, Hamad. Then there is a question from Mosi. Mosi, do you want to ask your question? Okay, the mic does not work. So the question of Mosi is, I'm not sure I understand the question exactly. It's about, I don't know, the use of coupled RIS. It's easier to implement than star RIS? I don't know what you mean by coupled RIS.
I'm not quite sure either. Maybe you can add a little bit more comment, but I guess what you mean by coupled RIS would be maybe, is it the group RIS where no signals coming in at one element? And
Hello, sorry, can you hear me now?
Yes,
Yeah.
mostly we can hear you. Go ahead.
I read in the papers about the SIG that there are two implementations. One is the coupled one, that the phase shift of the front and back are related to each other. I mean, the summation should be, I don't know, pi or something like that. There is some linear relationship between the phase shift in front and back of the IRS for the star. And there is another one which is decoupled that also you mentioned that there is no, I mean, both of the phase can be arbitrarily anything. But I read somewhere in the literature that the decoupled one is easier to implement based on the physical implementation. But I'm not sure if they are true, if they are correct or not. I just want to ask your opinion.
Yeah, good question. I think what you mean is that for the coupled one, it means that the phase at the front of the service is somehow related to the phase at the back.
Exactly.
Decoupled, they can be completely different.
Exactly.
Yeah. So my guess is that for the coupled one, maybe I think the key here is the number of switches that you would need inside the star implementation. Like the one that we have shown there, we need two for reflection and two for transmission, so quite a few switches. Probably the coupled one may actually, you might be able to get away with less switches, and so the loss through it would be less. So just from my intuition on, I might not have enough information, but I would actually guess maybe the coupled star RIS may actually be easier to make than the decoupled one.
Thank you. Thanks a lot.
Yeah.
Thank you, Mosi. Any other questions? Anyone last question? So maybe last question on my side. So Ross, how do you see this implementation of these beyond diagonal RIS, where we have many different architectures?
Yes.
And we have those architectures where you have those pre-connected architectures, for instance, where we show this is the smallest number of elements you need to connect while still achieving the same performance as if they are fully connected. But nevertheless, you would need to have more than just this pi network of these two elements that you showed.
So this is like the block diagonal type RIS, I think you're referring to.
Block diagonal is one of them, but there are other architectures. Yes, so you need to connect more than just two elements together. So,
it's certainly going to be a challenge to make them. I don't have any initial comment. I would certainly think that if you had four, say, RES reflecting one with 4 elements, and then you have that probably with a block diagonal of 2 by 2, so that's 4 elements where you can recouple the energy into. I would guess it's probably feasible to probably make one. We are starting to look at that particular structure. I'm not sure how many you need to be connected together, but I think in a limited number of connections, maybe 2 by 2, 3 by 3 elements may be possible if we do the design carefully.
Okay, lots of interesting research problem ahead.
Yes. Well, it's good actually. The system results then motivate people to make the devices, and then there are more challenges when you make them. So it brings interesting things.
Excellent. Great. Thank you very much, Ross, for the very inspiring and informative talk. We will stop here. So we have recorded the presentation, the talk today. So we will put this on the BD-RIS webpage as usual for people to access and watch it. After asking, of course, Ross' approval.
That's fine. If anybody would like a copy of the slides, just email me and I'm quite happy to send them to you as well.
Right. Very good. Thank you, Ross. And with this, thank you, everybody. I think we'll have our next talk I'm not sure when it is, Matteo. I think maybe in 2 weeks from now or so. But we're going to have a fifth talk coming in this webinar series very, very, very soon. So looking forward to seeing you at the next talk. And thank you again, Ross, for the great talk. Thank you all.
Thank you, Bruno, for organization, and Matteo as well.
Thank you all. Bye-bye.